Right, good afternoon, everyone. Thank you all for joining us today for the SANCOLD YPF webinar on high floodline modeling. I'm Ashley Kutsia, the YPF chair at SANCOLD, and I'm thrilled to welcome such a diverse group of professionals and students to this important session. High floodline modeling is a critical aspect of flood risk management, and today's speakers will share their valuable insights on this topic. We are fortunate to have with us two distinguished presenters from the Department of Water and Sanitation, also known as DWS, Brandon Lee Eli and Ernest Oakes. First, allow me to introduce Brandon Lee Eli, a 28-year-old candidate civil engineer at DWS. Brandon grew up in Grassy Park in Cape Town and excelled as the top student at Grassy Park High School. Initially aspiring to be a professional soccer player, his talent in STEM subjects, especially mathematics and physical science, led him to pursue a career in civil engineering. He earned his BEng Civil degree from the University of Stellenbosch in 2020, and Brandon joined the DWS in October 2021. He's currently working towards his professional registration with EXA. His journey and passion for engineering are truly inspiring, and we look forward to hearing his insights today. Next, we have Ernest Oakes, a specialist manager at the DWS with over 12 years of experience in water resource science. Ernest specializes in flood and water resource hydrology and hydraulic flood simulations. His extensive experience spans both the private and public sectors, where he has worked on crucial projects, including dam flood estimation for dam design, dam safety surveillance, and the determination of flood risk areas. Additionally, Ernest has overseen hydrological simulations and long-term yield assessments. His wealth of experience and knowledge will undoubtedly provide us with critical insights into today's topic. Before we begin, just a few quick housekeeping notes. The mics will be muted during the presentation to avoid any background noise. If you have any questions, you're welcome to type them in the chat or wait until the question and answer session where you can raise your hand. The session is being recorded and will be shared to all attendees after the event. So now, without further ado, I would like to welcome Brandon to share his presentation and start off the session. Thank you.
Good day, everyone. Ashley, can you just confirm that my presentation is visible?
Yes, I can hear you clearly and your presentation is visible.
Okay. Can I begin?
Yes, thank you.
Okay, thank you. Good day, everyone. I hope that you are all doing well. Today, my presentation is on how to conduct an indicative study on the 1 in 100-year high flood line of a dam. Firstly, I will give an introduction to myself. Thereafter, I will explain what the high flood line is and why it is necessary to determine the high flood line of a dam. I will then explain how the buffer strip of a dam is determined from the high flood line. I will then discuss the difference between an indicative and a confirmed high flood line. Thereafter, I will present one of the high flood line studies I did which was for Shishegu Dam, where I will discuss the hand calculations and egress models that I used to determine the high flood line. I will then do a comparison of all the results I obtained and end with a conclusion. As previously mentioned, my name is Brandon Lee Eli. I obtained my civil engineering degree from the University of Stellenbosch in the year 2020, after which I joined the Department of Water and Sanitation in October 2021. I am currently employed as a candidate civil engineer under Directorate Civil Engineering in Subdirectorate Open Channel Systems, where the main function of this component is the design of irrigation canals. So what is a high flood line? A high flood line represents the highest elevation reached by a free water surface during a particular flood event. This is a crucial parameter to determine when considering the flood risk management and dam safety of a dam. Why is it necessary to determine the high flood line of a dam? The construction of a dam within a river poses a risk of the dam causing flooding. When a flood passes through the dam during a flood event, the dam wall constructed in the riverbed will cause a backwater, causing the water levels upstream of the dam wall to rise. Consequently, infrastructure located on the banks of the dam could sustain flood damage as a result of the rise in water levels during the flood. Therefore, the indication of a high flood line is necessary to warn the public of the potential maximum elevation which could be reached by the water in the dam during a flood, particularly the 1 in 100-year flood, so that they can stay clear of this area and not build any infrastructure within the demarcated area. According to Chapter 12 of the National Water Act, the owner of a dam must ensure that the dam's potential to cause harm to the public is reduced, the dam's potential to cause damage to infrastructure is reduced, and the potential damage to resource quality is reduced. Section 144 of Chapter 14 of the National Water Act also states that the 1 in 100-year high flood line of a dam must be indicated on plan drawings and made available to the public. Since the Department of Water and Sanitation is the custodian of most of the dams in South Africa, we are obligated to adhere to these regulations as stated in the National Water Act. The figure shown demonstrates why it is necessary to indicate the high flood line of a dam. Looking at the figure, it can be seen that when you have infrastructure located within the high flood line, it has a higher risk of sustaining damage during the 1 in 100-year flood event. And when infrastructure is located outside of the high flood line, it has a lower risk of sustaining damage during the 1 in 100-year flood event. This example shows how the indication of a high flood line of a dam can alert the public of hazardous areas around the dam. Once the 1 in 100-year high flood line of the dam is determined for the dam, the department also estimates a buffer strip for extra safety. According to the policy and guidelines for the acquisition of land rights at the departmental dams, the buffer strip for a dam is determined as follows. From the calculated high flood line, you will either go 1.5 meters vertically upwards from the high flood line or at least 15 meters horizontally outside of the high flood line. Whichever results in a greater horizontal distance would indicate the position of the buffer strip. For example, if you were to take a cross-section of your dam, as indicated by the red line on the figure on the left, it will look something like the figure shown on the right, where the blue line represents the maximum level of water in the dam caused by the 1 in 100-year flood. From this water surface elevation, you will go 1.5 meters vertically upwards or 15 meters horizontally outside of the water level and choose the buffer strip based on whichever of the two results in a greater horizontal distance. It can be seen from this example that the 15 meters results in a greater horizontal distance and will therefore indicate the position of the buffer strip. The reasons for adding a buffer strip to the high flood line of a dam are as follows. Changes in flood hydrology of the dam. It could be that the 1 in 100-year flood peak of the dam changes over the years, which could result in a higher flood line. It minimizes claims against the department for flood damage. It protects the quality of the water resource. The inclusion of the buffer strip will result in developments being built further away from the dam, thus reducing the probability of water in the dam being polluted by communities close by. You could have sediment accumulation in the dam basin over the years, which will reduce the storage of the dam and potentially increase the level of the high flood line. It allows access to the dam during normal operation hours and extreme flood events for possible rescue operations. The figure shown is just an example of something I experienced myself when I was deployed to KZN to assess flood damage to various water infrastructure after the flood event which occurred in the province in April 2022. What we have here is a pump station which is located within the 1 in 100-year high flood line of a nearby watercourse, which ended up sustaining damage after the flood event. The slide indicates some of the damages to the infrastructure where the pump station was flooded, and you can also see the settlement cracks which occurred within the walls of the pump station after the supporting soil of the infrastructure became saturated, reducing the strength properties of the soil and resulting in settlement of the soil. Before discussing one of the indicative high floodline studies I conducted, I will first highlight the difference between an indicative and a confirmed high floodline. For an indicative high floodline, you perform your hydraulic calculations and modeling based on information which is made readily available to you. Assumptions are made for data which is not readily available, but still required to perform the hydraulic calculations and hydraulic modeling. Therefore, the data used is not highly reliable. However, a sensitivity analysis is done on parameters which are assumed to provide more confidence in these assumptions. For a confirmed high floodline, less assumptions are made and more accurate data is used to perform the hydraulic calculations and modeling. For example, if you have to do a high floodline for a dam and the discharge coefficient of the dam spillway is unknown, you will have to do a physical model study of the dam to help determine this parameter more accurately. Whereas with the indicative high floodline, you will assume a lower and upper bound for this parameter and then do a sensitivity analysis on this assumption to test the correctness of this assumption. The diagram shown summarizes the methodology I used to conduct the indicative high floodline study. I first collected data, the data which are required for the high floodline study. After collecting the data, I used hydrodynamic engineering software to generate the high floodline and perform man calculations to obtain the high floodline. The engineering software I used was ACRES version 6.0, where I created both a 1D and 2D ACRES model to generate the high flood line, and the hand calculations I used to obtain the high flood line was a flood routing. I then compared the water surface elevations produced by each of these analysis methods and chose the highest water surface elevation as the indicative high flood line study for the dam. I will now discuss the indicative high floodline study I did for the 1 in 100-year high floodline for Shishegu Dam. Shishegu Dam is an earthfill embankment dam which is located on the Blood River, approximately 12 kilometers northwest of Polokwane in the Limpopo province. The dam has a wall height of 13.1 meters and has a significant hazardous potential and is therefore classified as a Category 2 dam. As previously mentioned, this was an indicative study. Therefore, I used information which was readily available to me. Furthermore, I had to make assumptions for parameters which were required to conduct the study, but was not readily available. The limitations of the study was that I did not account for sediment accumulation in the dam, as there was no sediment survey available. However, since the dam was of medium size, the inclusion of sediment buildup would not have much of an effect on the high flood line. This is because when the flood wave enters the dam, it is assumed that the dam is at full supply level, resulting in minimum interaction between the flood wave and the basin of the dam. Also, the effect of sediment accumulation would be accounted for when the buffer strip for the dam is determined from the high flood line. For small dams, this parameter would have to be considered, as there would be interaction between the flood wave and the dam basin, causing the sediment accumulation to have a significant effect on the high flood line. The survey data which was provided to me only contained contours from where the river entered the dam. Therefore, sediment accumulation where the river enters the dam was not included in the study, which could cause an increase in water levels upstream of the entrance. Therefore, the study was only conducted between the entrance of the dam and a few meters downstream of the dam. The table shown indicates the data which was readily available to me and where I obtained the information that I used. So from the 1 in 100-year peak flow for the dam and the time of concentration for the flood, I obtained from the flood frequency analysis report for Shishegu Dam, which was conducted in 2020 by Subdirectorate Flood Studies within the department. The full supply level of the dam, non-overspill crest level of the dam, full supply capacity, full supply area of the dam, and the length of the spillway and spillway type I obtained from the Dam Safety Evaluation Report, which was conducted in 2015 by Subdirectorate Dam Safety and Surveillance within the department. The capacity survey data and bathymetric data for the dam I obtained from Subdirectorate Land Matters and Information Management, who was the client for the project. And the discharge coefficient of the spillway I obtained from a model study report, which was conducted in 2016 by Subdirectorate Open Channel Systems. For parameters which were not readily available, I had to make the following assumptions. In addition to the 1.4 discharge coefficient I obtained from the model study report, I assumed another discharge coefficient of 1.6. This was to test the sensitivity of my calculations to this parameter. It should be noted that when making an assumption for this parameter, you must take into consideration the type of spillway you are dealing with. Each spillway type has a range for the discharge coefficient. If no information is provided regarding the discharge coefficient of the spillway, the most conservative approach would be to perform your hydraulic calculations and hydraulic models for the lower and upper bound values given for the specific spillway, and then do a sensitivity analysis to assess the influence of this parameter has on your analysis. Sorry. For the Manning's roughness value, I assumed a lower and upper bound value of 0.03 and 0.06 respectively, where the lower bound value is applicable to floodplains with light bush and trees, and the upper bound value is applicable to floodplains with stones and weeds. As with the discharge coefficient, I assumed two values for this parameter to do a sensitivity analysis to test how much of an influence this parameter had on my hydraulic calculations and models. I assumed that the dam was at full supply level by the time the flood wave entered the dam. For the flow hydrograph, I assumed a 3TC triangle with a base flow of 10% of the 1 in 100-year flood peak of the dam, which was reached after time equivalent to 1 TC and subsided after time equivalent to 2 TC. Before setting up my hydraulic models, I first did hand calculations to determine the high flood line of the dam. As previously mentioned, I performed hand calculations in the form of a flood routing analysis. I did a flood routing analysis for both discharge coefficients, for both given discharge coefficient and the assumed discharge coefficient. The input parameters I used to do the flood routing was the assumed inflow hydrograph, which was previously mentioned, and the area capacity data I received from the client. After running the calculations, I obtained a maximum water surface elevation of 1,237.013 meters, which was for my discharge 1.4 discharge coefficient. After obtaining the high flood line from my hand calculations, I proceeded to set up my ECRES models. ECRES requires you to have the rain data of your dam basin in order to do a model to generate the high flood line of the dam. If bathymetry data is not available, you can assume a bathymetry for the dam if the dam is of medium or large size. This is because at the start of the flood event, the dam is assumed to be at full supply level, resulting in minimum interaction between your dam basin and the flood wave. This assumption is not applicable for small dams, as there would be a significant interaction between the dam basin and the flood wave. For the assumed bathymetry, you can assume either a triangular or a rectangular bucket with an average depth, which is equivalent to your full supply volume of your dam divided by your full supply area of your dam. Please note that this should be the last resort should you be required to provide the high flood line urgently and not have the time to conduct a bathymetric survey for your dam. There are various approaches which can be used to model the bathymetry of the dam if this data is not made available to you. The following slides describes the step-by-step process I use to model the bathymetry of the dam. Due to time constraints, I will not go through all the steps and provide a brief summary of the approach I use. Please note that this is not the method I used for my indicative high floodline study, as the actual bathymetric data for the dam was provided to me by the client. Firstly, I go onto the CDNGI website where I download contours of the dam where the lowest contour level of the dam provided is usually the full supply level of the dam. The contour data on the CDNGI website does not provide contours below a water surface. Hence, the lowest contour level provided for the dam is the full supply level of the dam. The following steps just explains how you would obtain the contour data from CDNGI, which I'll just skim through. Once you obtain your contour data from CDNGI, you can then import it into QGIS. And the following steps that I'll skim through explains how to do that. Since I'm only interested in the contours around the dam, I clip these contours so that I can exclude the rest of the contour data. I do this by drawing a polygon around my dam and then using the clip tool in QGIS to extract the contour data within the perimeter of the polygon. All the contour data outside of the perimeter of the polygon will be excluded. The following steps that I'll skim through explains how you extract the contour data that you require. After applying the clip tool, a shapefile will now be created containing the contours which were located within the perimeter of the polygon. I then save this shapefile in a chosen location and export the shapefile to Civil 3D, where I will generate contours for the dam basin and then create a digital elevation model for the dam, which I then import into ECRES. The following steps will show you how you save this shapefile. Once I created the shapefile for my dam contours in QGIS, I create a surface from the data in Civil 3D. In Civil 3D, I click the drop-down arrow next to surfaces and select create surface from GIS data. You'll then be prompted to enter specific information regarding the data, which is explained in the steps which I'll skim through. Once you have entered all the necessary information, a surface will be created from the contours which were clipped in QGIS as shown in the figure. I then generate contours below the full supply level of the dam by using the offset function in Civil 3D, where the lowest elevation in the basin will be the NOC, the non-observable crest level of the dam, minus the average depth, which is calculated as discussed previously. You then create a digital elevation model of the surface, which is explained in these steps. As previously mentioned, I used ECRES to generate the high flood line of the dam. In addition to the hand calculations that I did, the version of ECRES which I used was ECRES version 6.0, where I created both a 1D and 2D model of the dam. The figure shown illustrates the difference between the 1D and 2D ECRES models, where with the 1D model, a river is drawn through your dam along with cross sections as shown by the green lines. And the 2D model consists of a 2D mesh which is drawn over the dam. There are 5 main steps to create a ECRES project, which are as follows: starting a new project, entering geometric data, entering flow data and boundary conditions, performing the hydraulic calculations, and then viewing and publishing of the results. I will now discuss how I set up my 1D ECRES model. When you open ECRES, the ECRES software, the figure at the top will show up, which is the main window of the software. For creating a new project, I set the unit system of the software to SI units. To do this, in the main window, I select options and then select unit system. Once unit system is selected, the window shown will pop up. I then set the unit system to SI units and check the box next to the set as default for new projects to ensure that all future projects which will be created in the software will be set to SI units. As I set the SI units of the system, I create a new project. I did this by selecting the file in the main window and then selected new project. Once the new project was selected, I saved the project in the location of my choice and gave the project a name. Once the project was created, I proceeded to create a geometry for my project. To do this, I selected the geometry editor tool, which is indicated by the icon in the red circle over here. Once I selected this tool, the window shown below popped up. In this window, I selected File and then New Geometry Data. Once New Geometry Data was selected, the window shown popped up where I chose the location to save my geometry and give the geometry a name and then selected OK. After I created the geometry for my dam, I proceeded to add the terrain of my dam to the model. To do this, I had to access the RAS Mapper interface. I did this by selecting the red icon, the icon circled in red in the main window. Once this icon was selected in the window shown on the left over here popped up. I then selected project and then create new RAS terrain. Once I selected this, the window shown on the right would popped up. I then clicked on the plus sign in the red square to add the terrain to my model and selected create. Once this is done, the terrain will show in the RAS Mapper interface as shown in the figure. After adding my terrain, I proceeded to draw the river through my dam. I did this by right-clicking on the river option underneath the geometry I created and selected Edit Geometry. When in the Edit Geometry mode, the following tools are available to you. You can use the pencil to draw objects on the terrain. And then you can use this icon over here to select objects to auto delete them. And then you can also use this icon over here, which is used to stop editing and to save changes to your geometry. After selecting edit geometry, I use the pencil tool to draw the river through my dam. I drew the river in the direction of flow from the point where the river entered the dam up until downstream of the dam wall. Once I drew in the river, I gave the river a name and also a reach name and clicked OK. After drawing in the river, I selected the red dot to stop editing and save the changes to my geometry. After I drew my river, I saved the changes and proceeded to add cross sections to my dam. I did this by right-clicking on cross sections option and then selecting edit geometry. I then used the pencil tool to draw my cross sections, which are indicated by the green lines in the figure shown. I drew the cross sections from left to right. From left to right when looking downstream of my dam or in the direction of flow. And also drew the cross sections perpendicular to the contours of the dam where possible. After drawing in my cross sections, I proceeded to add the Manning's roughness values to each cross section. I did this by going back to the main window and selecting the geometry editor interface. Once in the interface, I selected tables and then selected Manning's and OK values. In the window shown then popped up where I entered the Manning's roughness values for my cross sections. I used the same Manning's roughness values for the floodplains and the main channel of the dam. The accuracy of the Manning's roughness value used for the main channel won't have much of an effect on the results since there's not much interaction between the flood wave and the dam basin. After inserting the Manning's roughness value for all the cross sections, I proceeded to input the spillway of my dam in the model. I modeled the spillway by using an inline structure tool in ACRES and assumed that the spillway behaved as a weir since the standard weir equation is used to calculate flow over the spillway. I added the inline structure by going to the geometry editing interface and selecting the inline structure tool as shown over here. The window shown on the left then popped up where I selected options and then add inline structure. I then specified the station number for the inline structure. It is important to note that when you create an inline structure and specify the station number of the structure, the cross section of the in which the inline structure is placed takes up the shape of the cross section located just upstream of the inline structure. Therefore, if you had a cross section with a station number 69 located downstream and a cross section with a station number 67 located upstream, and you give your inline structure a station number of 68, it will take up the shape of the cross section 67. I then selected the wear embankment tool to specify the properties of the spillway, such as the elevations, discharge coefficient, and spillway shape. When specifying the stations and elevations of the inline structure, it is important to ensure that the non-overspill crest level, full supply level of the dam, and the length of the spillway is inserted correctly. I inserted the assumed discharge coefficient value as previously uh, for the dam spillway, as previously mentioned, and chose the weir crest shape as the broad crested since the dam had a bywash spillway. A crest determines the high flood line of the dam through iterative calculations, and therefore boundary conditions are set within the model to allow a crest to begin the calculations required to determine the high flood line. Since the inflow hydrograph depicts that the flow changes over time, the unsteady flow data option was used to insert the boundary conditions for the model. I entered the boundary condition data into the model by selecting the unsteady flow data icon shown over here in the main window. The window shown on the left then popped up where I created a new unsteady flow file and saved it in a chosen location. As an upstream boundary condition, the assumed inflow hydrograph, as previously discussed, was inserted into the model. As a downstream boundary condition, the slope of the terrain in close proximity to the last cross-section located downstream was used. The slope was measured directly on the terrain using the measuring tool in a RAS mapper. Initial conditions were also set into the model to ensure that the dam was at full supply level at the start of the flood event. As an initial flow, I inserted the base flow, which was used in the inflow hydrograph, which was 10% of the 1 in 100-year peak flow. I've noticed that using the base flow doesn't always ensure that your dam is at full supply level. Therefore, it becomes an iterative process where you will have to change the initial flow accordingly until you obtain a flow which ensures that your dam is at full supply level at the start of the flood event. After specifying the boundary conditions for the model, I proceeded to create an unsteady flow analysis for the model. I did this by selecting the unsteady flow analysis icon in the main window as shown over here, and then creating a unsteady flow plan as shown in the figures and save the plan in the chosen location. The model was set up to run for a total of 8 hours, and it is important to note that the simulation runtime and the inflow hydrograph was set to run for the same amount of hours and on the same dates. If this information is not the same, your model will not run. Another important parameter to note in this window is the computation interval. The smaller the computation interval, the more accurate your results will be. The computation interval can also help in producing a more stable model should your model go unstable. If the model goes unstable, the computation interval can be reduced to produce a more stable model. There are two numerical solutions which can be used to run a 1D unsteady analysis, which is the finite difference and the finite volume. I use the finite volume numerical solution because it can handle cross sections going dry when the finite difference cannot. It can produce a stable model during low flow computations. It produces a stable model for mixed flow regimes, and it can handle extremely rapid rising hydrographs without going unstable. Therefore, in summary, it has a greater probability producing a more stable model compared to the finite difference method. You can run your model using the finite difference method, but should this method produce an unstable model, you can always try and run your model with the finite volume to produce a more stable model. Once the model ran successfully and a stable model was produced, I proceeded to obtain the results for the high floodline. To obtain the maximum water surface elevation in the RASMapper interface, under results, I tick the checkbox next to the water surface elevation. I then clicked on max as shown in the red circle over here, and then hovered my mouse over the dam to obtain the maximum water surface elevation as shown in the red circle. I also added profile lines in my dam to obtain the water surface elevations at different sections in the dam. I did this by right-clicking on the profile lines option under features and then selecting edit layer. I then drew my profile line at the areas of concern, gave the profile line a name, and then clicked OK. In the bottom left corner um, of the RASMapper interface, I selected the profile line option and right-clicked on the profile line I created. Under plot profile, I then selected water surface elevation to obtain the water surface elevation at that section of the dam. The figure indicates the water surface elevations I obtained for the profile lines I created in the dam basin. I then obtained the flood inundation boundary from ECRES by right-clicking on the results and selecting Manage Result Maps. Then next to Plan, I clicked Add New Map. I then selected Inundation Boundary under Map Type and under Unsteady Profile, I selected Maximum, and under Stored, I selected Polygon Boundary at Value, and then thereafter I selected Add Map. After which the inundation boundary appeared as a shapefile under the result layers. I then imported the inundation boundary into Civil 3D along with the background imagery to obtain the flood inundation map shown in the figure. After obtaining the results for my 1D model, I proceeded to set up my 2D egress model. I first drew my 2D flow area mesh over the dam. When drawing the mesh, it is important to ensure that the edges of the perimeter of the mesh at least include the NOC of the dam. You may include contours that are higher than the NOC level to be more conservative. This is to ensure that if the high flood line reaches the NOC of the dam or any elevation higher than that, these contours will be included in the mesh so that the water surface elevation can be computed in ECRES. To draw in the 2D mesh under the 2D flow areas, I right-clicked on parameters and then selected edit geometry. I then proceeded to draw in the 2D flow area around my dam. And then when I was done drawing the 2D flow area, I double-clicked and was prompted to give the flow area a name. So I specified a name for the flow area. The window shown over here popped up, where I specified the size of the mesh in the 2D flow area and the Manning's roughness value of the mesh. I used a 7 by 7 meter mesh and used the Manning's roughness values, which I assumed as previously discussed. After specifying the parameters of the mesh, I selected generate computation points. Please note that the smaller the mesh size you use, the more accurate your results will be. However, a smaller mesh will take your model a longer time to compute. The 7 by 7 meter specification for the dy and dx in the mesh setup of the mesh was used to set the size of each cell within the flow area of the mesh to 7 by 7 meters. I included break lines into my model to accurately predict the behavior of the flow at certain areas of my dam. A break line is usually added where there is a barrier to flow or where there is a control of flow or direction. I therefore added break lines at the spillway, the non-overspill crest level, and the full supply level of my dam to create a finer mesh in these regions compared to the global mesh to provide more accurate results in these areas of concern. To add a break line under 2D flow areas, I right-clicked on break lines and selected edit geometry. I then proceeded to draw my break lines on my terrain in the areas of concern. The figure shown indicates the break line which I added at the non-overspill crest level of my dam. To specify the mesh size of the break lines, I right-clicked on break lines and selected the edit break line properties option. The window shown then popped up where I then specified the size of my mesh for the break line, where I used a 2 by 2 meter mesh. After specifying the size of my mesh, I selected info selected as break line to add this mesh size to the break lines in the global mesh. The spillway of my dam incorporated into my model using the SA2D connection tool in ECRES. This tool is used to model hydraulic structures in 2D flow areas and ensures that the cell faces connected to the hydraulic structure is perpendicular to the flow. To add a SA2D connection under 2D flow areas, I right-clicked on SA2D connection and selected edit geometry. I then drew my SA2D connection directly on my terrain where my spillway was positioned. When drawing the structure, it is important to ensure that it is drawn from left to right when looking downstream of the dam or in the direction of flow. Once the SA2D connection was drawn in, I proceeded to refine the mesh at the location of the spillway, and I did this by enforcing a break line in this location. I did this by right-clicking on the SA2D connection and then selecting the Edit 2D connection break line properties. The window shown on the left then popped up where I specified the 2 meter by 2 meter mesh for the spillway and enforced it as a break line to add this refined mesh to the global mesh. Once I drew the SA2D connection on the terrain in a RAS mapper, I specified the shape and properties of the spillway in the geometry editor interface. I did this by selecting the SA2D connection tool and then selected weir embankment tool to specify the length of the spillway, full supply level, and non-overspill crest level of the dam, the discharge coefficient of the spillway, and the spillway type, as previously illustrated with the 1D model. Before entering the data for the boundary conditions for the 2D model, they have to be drawn. They have to physically be drawn in the 2D flow area as a boundary condition line. I did this by right-clicking on boundary condition lines under 2D flow areas and selected edit geometry. The upstream boundary condition I drew at the start of the 2D flow area where the river enters the dam, and the downstream boundary condition line I drew at the end of the mesh downstream of the dam wall. Once the boundary condition lines were drawn in, I inserted my data for the upstream and downstream boundary conditions as indicated with the 1D model. For the initial condition for my 2D model, I inserted the full supply level of my dam to ensure that my dam was at full supply level at the start of the flood event. I then set up my unsteady flow analysis as shown with a 1D model. There are two numerical solutions to consider for the 2D model, which is diffusion wave equations and shallow water equations. The diffusion wave equation is the default solution which is used for computations with 2D models. However, shallow water equations accounts for more losses in the system and therefore produces more accurate results. It is recommended to first run your model using the diffusion wave equations, as it is easier to produce a more stable model using this method. Once a stable model is produced, the model should then be run using the shallow water wave equations. And if there's a significant difference between the results produced between the two, then the shallow water equation result should be used. After running my model and obtaining my water surface elevation, the maximum water surface elevation for my 2D model, I plotted the inundation map for the 2D model as shown in the figure. After obtaining the water surface elevations for all my analyses for my 1D and 2D acres models, I compared my model results by taking the difference between the water surface elevations for each analysis, which was done for my 1D and 2D models. From the results, it can be seen that there is a minimal difference between the 1D and 2D model results, which provided confidence in my model results. I then compared the maximum water surface elevation produced by my flood routing 1D and 2D acres models by taking the difference between my flood routing results and the acres model results. From the results, it can also be seen that there was a minimum difference between my N calculations and my acres models, which also provided confidence in my results. I then used the maximum water surface elevation produced by my 2D acres model as the indicative 1 in 100-year high flood line for my dam, as this was the highest water surface elevation which was produced out of all my analyses and was therefore the most conservative high flood line to use in terms of public safety. Thank you.
Thank you so much, Brandon, for that very detailed presentation. I'm sure there are a lot of people in the audience that are going to use all those steps, and you're welcome to go and look at the recording later on and pause as needed. So now I would like to just give, we're not going to take questions now, sorry, we need to take them at the end. So if we can please give Ernest a chance to present his case study. Thank you, Ernest.
Thank you, Ashley. Could you just confirm that you can see my presentation?
Okay, not yet. I can hear you clearly though.
Okay, let me just share it again. Can you see it now?
Yes, we can see it. Thank
Fantastic. Okay, awesome. Okay, thank you very much, Mr. Chair, and for Brandon for your presentation, and to the audience for joining. Again, Ashley, thank you very much for that very well embellished introduction. It's actually saved me a bit of time on this slide. So I'll just introduce myself quickly. My name is Ernest Oakes, and I'm just going to take you through a study that I did back in 2022 on the high flood line assessment for Tluwa Dam. So just a bit of an introduction about to recap on some of the points that Brandon mentioned about the importance of high flood lines. So it is stipulated in the National Water Act that high flood lines need to be provided to the public in an acceptable form, either in the form of plans or maps or the other such sources. Also important to note that the DWS is the custodian of South Africa's water resources, and we are obliged to make floodlines available to the public. These floodlines also pertain and help us either maintaining or improving our infrastructure and help us to plan how to improve infrastructure going forward. And just interesting to note, although it's not critical for this presentation, tailwater analyses are also quite important for the exact same reasons, but they are basically undertaken with a focus on the downstream environment of a dam. There's just some background information about Tluwa Dam and why the study was undertaken. So some information about Tluwa Dam itself. It's actually a Category 3 structure located on the Tluwa River, about 1 kilometer northwest of Butterworth in the Eastern Cape Province. So what actually happened with this dam is that from the period 1972 up until 2022, 1972 up until 2020, my apologies, when we did 2 bathymetry surveys, amongst others, we found that the dam had actually lost a significant amount of its storage capacity. Now, the reason for that is because some of you may know that the soils in certain parts of the country, especially in the Eastern Cape, are quite dispersive and prone to erosion quite easily. So they can be basically considered to be quite erosive soils. So that's actually part of one of the main reasons as to why this dam has actually lost so much of its storage capacity. So our colleagues at the DWS, specifically our colleagues in the dam design section, undertook a very detailed assessment of all sorts of options to look into how we could reclaim the storage. And after numerous options that were considered, it was basically decided that what would be a good short to medium term solution is to raise the spillway level and the full supply level by 1.5 meters, and then widen the spillway on the right bank by 20 meters. This would basically give us some time for the next few years or decades to implement a more long-term solution. And just important to note that the non-overspill crest is also going to be, or I should say, is planned to be raised by 1.2 meters to account for those additional floods and the increased flood water levels, I should say, as a result of the changes in the dam. And the last bullet point, as well as a sub point, so basically some factors that we had to consider for the hydraulic study that we're going to be discussing now, as well as some of the hand calcs as well. It's interesting to note with all of these interventions, the storage capacity will basically be increased again from 0.42 to 1.12, just buying us some more time and buying us some more storage before we can implement a more long-term solution. Now, some information about Kruger Dam itself. As I indicated, it's in the in the Eastern Cape, quite close to the town of Butterworth on the Kruger River. So we can see that there's the town just close by, and just for interest's sake, this little weir here, which is actually not important for the study that we're discussing today, but it was important for the flood frequency analyses, which I'll allude to a bit later on. And then this is just a bit of a zoom in on the dam, as well as the surrounding infrastructure to the east, I should say, to the south of the dam, and that weir again. On to the information that was basically fed into the study. So we have two recent flood frequency analyses were undertaken for the study. One being the study undertaken by Roux et al. In 2016, and then later by Ramnaran et al. In 2021 as part of dam safety requirements. So some of you may know that the Department of Water and Sanitation frequently undertakes flood frequency analyses to assist various colleagues, especially those in dam safety, with their ongoing dam safety evaluations. So this actually forms part of those inputs. And then they doubled up as an input for Kruger Dam as well. What happened thereafter was Oberholzer et al. In 2020 and in 2021 undertook very important work pertaining to the improvements of the dam. The issue, or the side issue I should rather say, was the work of Oberholzer actually took place, I should rather say, before the finalization of the report that was undertaken by Ramnaran et al. In 2021. And as a result, the findings by Roux et al. Were implemented. But the advantage of the way things played out was that the study by Ramnaran et al., which actually took place a bit more recently, showed that the flood peaks that were estimated by Roux et al. Were actually adequate for the purposes of this particular study, and may even account for some uncertainty due to the fact that the peaks are slightly higher. So another thing that you may know is that when a flood routing analysis is done, we need to, where possible, assume and look into the use of more than one flood hydrograph. So there'll generally be one peak, but there's a variety of ways to route that peak through the structure in question. So Roux et al. Proposed a series of flood hydrographs for routing purposes, which were basically analyzed through a series of hand calculations to see which one of them would be the most conservative towards risk within reason. So we basically used some equations that were basically documented in Chadwick et al. In 2013, as well as the post-developed dammed characteristics to account for post-developed site conditions. And what we found was that when going through the report, that Roux et al. Basically proposed a series of 4 observed hydrographs, as well as a series of estimated hydrographs as well. So as per the norm, what we did was we basically took each one of those hydrographs, did some simple scaling to ensure that they all had a peak of 970, which is basically equal to the TC 100-year flood peak. We also considered the half TC and 2 TC 100-year flood peaks as well, so that we could basically use the half TC and 2 TC SUH hydrographs, just to include them as a bit of a sensitivity analysis as well. And then we basically found from this that the SUH TC and DRH TC flood hydrographs provided us with the highest water level from our simple hand calculations. We could have potentially gone with perhaps maybe the September 2002 or perhaps the November 1985 floods hydrographs, because those were observed flood hydrographs. But to be conservative towards risk, we decided to rather adapt the SUH-TC flood hydrograph. And some of you may know that the DRH, and I should rather say the SUH hydrograph tends to be a bit more conservative towards risk because it is a bit more, more of a voluminous type of hydrograph. This particular case was quite interesting that the two get the same water levels, but we decided to rather just be conservative and be a bit consistent with our conservative approach within reason and just use the SUH-TC flood hydrograph for routing purposes. And I was very fortunate with this study because we had contour information at half-meter intervals that was obtained from our survey office. So that actually helped cut out a lot of the pre-processing time that I needed to do and apply to be able to get this study underway. And then this is just a bit of a zoom in on the dam itself, showing you the contour information in and around the dam basin. So we can see, for those of you who know, this is actually a bit of a dream to work with. So I was actually quite fortunate. But the thing that we just need to consider is the fact that this basically shows what the site looks like under current site conditions, not under post-developed site conditions. So what we had to do is account for the fact that the spillway is going to be widened to increase the storage of the dam, and the spillway level is also going to be raised. So I was fortunate again, thanks to my colleagues, that there are detailed drawings both in PDF and in DWG format, which basically show how the earthworks is going to be implemented to ensure that the objective of the project is reached. So I'd just like to draw your attention to this drawing on the left-hand side, as well as all the excavation that you see here. My apologies, this drawing may be slightly pixelated, but there are elevations associated with the levels that you see here. And we can see that there's a wider spillway in this area here. What we also see is if we were to take a look at a different drawing, which shows what the spillway will look like if one were to stand in the Kluwer River and look upstream, we can see that we've got some information pertaining to the geometry of that spillway, which also needs to be accounted for in the hydraulic model. So using the DWG files that were provided to me by my colleagues, I was able to import them into ArcMap and then basically amend and improve my contour information to allow for post-developed site conditions to be undertaken and to be assessed. So essentially what I did was I took that excavation section, created a shapefile from it, and then cut out a section of the contours to allow me to insert this portion of the excavation earthworks, which we assume will basically be the case once the project has been completed. So I could basically undertake a hydraulic simulation that is as close to as possible to what the site will be like after the improvements have been undertaken. So we can see here that there is actually an approach channel, which will basically be incorporated into the whole earthworks, the spillway extension, as well as the return channel, which will be widened as a result of the increase in, or the need to increase the storage capacity. This is what that dam looked like after I applied the Topo Terraster tool in ArcMap to create a digital elevation model. And then after importing it into HECRAS, this is what that final dam looked like. So we can see there's quite a lot of detail all over the place, which is very, very useful for a study of this nature. And if we take a bit of a zoom in, we can actually see what the geometry of the basin and the surrounds look like, which is basically now going to be fed into that hydraulic model for determination of that 100-year. And my apologies. So something else just to take note of, as Brandon alluded to earlier on, the need to account for as much information as we can. So at the time of the study in 2022, the South African National Land Cover for 2020 was available on the Department of Environmental Affairs website. Unfortunately, the 2022 land cover wasn't available because that, as far as I can understand, was released, I think, toward the end of 2023 or earlier on this year. So the 2020 land cover was what we had available to us. So we needed to consider that for this particular study. And then in terms of the mesh, so what we did was we basically drew a mesh over the terrain file in HECRAS, and then through a series of simulations and sensitivity analyses, as well as through some guidance from my colleague, Mrs. Ashley Kutsia, we decided to do a mesh independent study. So we started off with a mesh size of 5 meters, and then we went down to 4, eventually 3, and then 2, and we found that we reached mesh independence at a cell resolution of 2 meters. But the one thing that I did notice when I was doing my mesh independent study is that the flood water levels did start to decrease. But they only decreased by 4 centimeters from the 5 meters mesh size down to the 2 meter mesh size. So there wasn't too much of a decrease. But just to be slightly conservative towards risk, I decided to rather leave the mesh size at 5 meters. Also because, as my colleague Brandon alluded to earlier on, if you start to increase the detail of your time steps or even your spatial information, your simulation times tend to get quite long. And because of the fact that we had to do numerous simulations just to do various testing for this particular project, and just to increase the turnaround time, we decided to rather leave the mesh cell size of 5 and then introduce a refinement region at the spillway area, where the spillway alignment was basically used as the break line. And we implemented a 1 meter refinement region with a width of 20 meters on either side of the spillway. So basically a total width of 40 meters in the downstream direction, which was quite a useful little exercise to ensure that we improve our model accuracy. And then the upstream boundary condition, which is basically located here, was basically where we brought in that 100-year flood peak with the SUHTC hydrograph proposed by Roux et al. In 2016. The energy slope was basically taken from the long section profile of the river. The downstream long section profile was used as the friction slope. And then we decided to use an initial condition of the dam being at full supply level to basically have an initial condition for that model to be, or I should say for the dam to be set at before the flood basically reached the dam and went through to the spillway. Again, thanks needs to be given to my colleagues Oberholzer et al. For the detailed information that I was able to gain access to for the spillway information, which was basically used, which was represented using a 2D storage area connection. So we can see that from that drawing that I showed you earlier on, which may have not been too clear, I was able to basically get an indication as to what geometric information needs to be put into the spillway to ensure that it is as close to, I should say, represented as close to reality as possible. What I also did was I introduced the theoretical rating discharge that was provided to me by our colleagues and used that as part of the information that was put into the boundary condition. And this was a bit of a learning exercise for me because when I was doing the project and doing my model iterations, I realized that it doesn't really matter what geometry you put into your inline structure, provided that you basically tell the model to use the rating table. So it was a learning exercise for me where I narrowed this, widened it, and no matter what I did, it provided I had this information, it would basically only use this as the control characteristics for that spillway. So just a bit of a point to note, please do test it yourselves and don't just take my word for it, please. And then onto the Clear Dam characteristics in terms of the hydraulic roughness. Again, just to reiterate, I used the 2020 land cover, basically a raster file that was then converted into a shape file. And then in the attribute table of that, I basically assigned a series of Manning's roughness coefficients to ensure that I tried as much as possible within reason to get a good representation of what the hydraulic roughness within the floodplain and within the dam itself would be for the simulation. And then this basically now is just basically onto the typical plan setup that I would have. So I am fortunate to say that I have done several hydraulic simulations before. But this was an interesting one where I had to do numerous hydraulic simulations. So the thing that I learned when I was doing this project was the importance of making sure that your geometry file, right, and your unsteady flow analysis file have got, how can I say, very concise and informative names so that you can easily chop and change between your simulations at a press of a button should you need to. Another thing that I learned is the importance of actually giving my plan names very detailed names, and also writing a bit of a story as to what the thought process was for the simulation in question. So I'll explain why this is a benefit, especially for me. I did the study in 2022, and then my colleague, Mrs. Ashley Kutsia, asked me to please present to you today. And I was able to easily go back, dig up the simulation, and quickly find the simulation which was considered as the final simulation. So that is just a bit of a point that I'd just like to get across. I hope that it will assist you in your simulations. And something else just to take note of is that the computation interval we felt would be fine if we just left it at 1 minute, which is actually quite a fine temporal resolution. We used a 10-minute interval for all the other hydraulic inputs. And then the hydrograph that was provided to us by Roux et al. Was actually at, if I remember correctly, at half-hour intervals. So just to increase the resolution of that hydrograph, we just did some simple linear interpolation to increase the number of ordinates from 30-minute intervals down to 2-minute intervals. And then we basically use that as one of the, I should say, the inflow hydrograph. And then through, again, thanks to Mrs. Ashley Kutsia for her input on this particular project, we decided to implement the current number because this basically allows for the model to adjust the computation time step to be smaller than the amount of time it takes for a water particle to move from one discrete grid point to the next. It basically optimizes the simulation for you. So that was actually quite a bit of a useful addition to the simulation. And then the last thing was, for this particular simulation, I decided to rather just stick with the diffuse wave equation. Based on my own experience, the diffuse wave equation does tend to give slightly more conservative results on the projects that I have worked on. And it does allow for a more stable model simulation, as well as the fact that it doesn't cause your model simulation times to be too long. So because of all the the factors we had to consider here, this was basically the combination of inputs as well as the other ones that we basically adopted for the study. And I'd just like to reiterate the point that, as Mr. Brandon Eli noted earlier on, the choice of equation that you use for your simulation is actually a case-by-case basis. So it is important to just, how can I say, treat each simulation as a unique experience and adapt your study accordingly within reason for your specific conditions. And then this is basically what those final results look like. So I was able to produce some pretty maps, so we can see that there's a series of graphs here. We've got the water depth, I should say we've got the water depth here, and the change in depth indicated by the different shades of blue. And then we've got the water surface elevation shown on the right-hand side, which is actually the final bit of information that we need to be able to disseminate to our colleagues. And then my colleague Brandon Eli noted earlier on, I also use a series of profile lines to be able to get some of the information pertaining to the water surface elevations within the dam at various sections, which was actually quite useful to be able to begin preparing the floodline and the information pertaining to the floodwater levels. And this is basically what the final product looked like. So a nice map with a whole lot of annotations indicating what the maximum surface water elevations are and what the extent of the floodline is based on the information that was made available to us for this study. I'd like to thank Ashley Kutsia for inviting me to present, my good colleague Brandon Eli for his very detailed presentation and for setting the scene, and to you, the audience, for listening to my presentation. Thank you very much.
Thank you so much, Ernest. I really appreciate that. Thank you, Brandon and Ernest, for your time and for coming out here and just showing us some of your work. It's always really interesting to see what DWS is doing, and also really useful for all of our colleagues that are still learning how to do these processes. But thank you so much for your time, and thank you for everyone who attended, because it really made it worth it. At some point we had 95 people watching. That really makes it worth our presenters' times. So I'm just going to give we still have some time for questions. So if you have a question, you can just raise your hand or you can type it into the chat. Any comments or questions are welcome. I'll just give a few minutes for people to think. All right, we have a hand from Alan. I'm going to allow your mic. Okay, Alan, you can unmute yourself and just ask your question or make your comment.
Thanks, Ashley. An excellent presentations to the presenters, and thanks for organizing. This isn't a question. This was sort of a question. We had over 80 people attending. 80 divided by 2 is 40. Can we have a keener interest in dams and maybe 40 applications for persons to be APPs on DWS and AN other dams? And if you can promote that, Ashley, thanks very much.
All right, thanks, Alan. I'll have to take that up with some of my colleagues. Thank you so much. We have another hand from Dr. Pluto. I'm allowing your mic. You can unmute yourself.
Okay, Ashley, thanks. Can you hear me?
Yes.
Excellent. Thank you very much. Thanks, Brandon and Ernst, for those presentations. Very informative. It's an area I would also still like to get some experience in, is, the new 2D modeling. Just two questions. The first one is for Brandon. You say you use the bywash spillway. You use the broad-crested weir equation for that. The bywash spillway, does it have a physical broad-crest concrete structure in it, or is it just the channel? Because then I think the broad-crest spillway equation might not be the appropriate one to use. That was just my question, that inside the bywash spillway, is there a physical concrete broad-crest structure built there? And the second question I have is for Ernst. I think I might have missed it in the beginning of his presentation, but was a bathymetry done for this? Oh, yes, no, sorry. I see that there was a bathymetry survey done for the dam. So he did have cross sections for all of the, or actually the contours throughout the dam basin was available. That's actually all I wanted to ask is all of those contour information is based on the new bathymetry. That's all I also wanted to ask. Thank you very much, Ashley.
All right, I'll give over to Brandon to answer first. You can just unmute yourself.
Yes, thank you for your question, Dr. Pluto. The spillway did actually have a concrete structure there, a broad crest concrete structure, and that's why I modeled the five spillway in the A-class model as a broad crested weir.
Okay, noted. Thank you.
Okay, Ernest.
Hi, thank you, Dr. Pluto, for your question. Yes, so the information that we had actually had the entire bathymetry available to us. So like I said during my presentation, I was very fortunate to have such detailed information available to me. There wasn't such a need to actually make any assumptions in that regard. Thank you.
Okay, no, thank you.
Okay, I'm going to just go to the chat. There was one before I take the next hand. So Naeem is asking, should DWS provide 1 in 100-year floodlines at all dams, and what about rivers? Anyone can answer that one.
Thank you, Ashley. So in answer to Naeem's question, I'll do my best to answer. So we are required to produce 100-year floodlines for all the dams. I think my colleague Brandon alluded to the fact that those floodlines actually help us establish purchase lines as well. But in terms of the rivers, from my experience, there isn't too much of a need to do the floodlines for rivers unless we're talking about systems such as the Vaal Orange River system, where flood control is done in that system, and we need to basically establish floodlines for stakeholders that have got their infrastructure very close to the river. And I think that rivers would basically there'd be a need to establish floodlines for human settlements and municipalities as well. So I don't want to pass the buck, but I do understand, as far as based on my own experience, that floodlines are basically at times, I think, a municipal function, so that they can basically inform the occupants of their municipalities as to where they can and cannot develop for their human settlements. I hope that is correct and answers your question. Thank you.
Thank you, Ernest. Yeah, I can just add a comment there. When it comes to water use license applications, it has to be accompanied by a floodline analysis. And this is when you have to show whether or not your infrastructure is within the floodline or not. And then you would have some sort of design implemented that will safeguard the infrastructure. So this is, then usually at a river or something like that. But it's DWS is the custodians of the dam. So specifically, that's our mandate. All right, so there's another question for Brandon. He's asking about what was the flow depth in your spillway. So it's not always clear who's asking. It's Maidi. He's asking to Brandon, what is the flow depth in your spillway? Brandon, do you remember?
Yeah, I was just trying to check now. Sorry. I did the study back in 2022, so I don't remember what the exact depth was, but it will just be subtracting the water surface elevation from your high flood line from your full supply level to get that flow depth over your spillway. Yeah, I hope that answers this question.
All right, thank you. Another question. Okay, the one is, can it be possible to input the exact dimensions of the dam in the model? And the second one, I've been having challenges generating the DM data from the bathymetry survey data. I'm going to give that one to Ernest to answer.
Okay, sorry, can I just read? Okay, in terms of the bathymetry data, so yeah, I'm not too sure what software you're using to generate your DEM. It can be a bit of a tricky process, but if you've got the information in DWG format, what you may need to consider doing is just making sure that your LO is correct in your data frame if you're using GIS. Unfortunately, I can't give many tips when it comes to using the engineering type of software, because I don't use it. The spatial environment that I work in is actually an ArcMap. But if you're most welcome to actually send me some emails and maybe we can have a discussion there. I'm more than happy to help out and just see what I can do to assist. The first question was getting the dimensions in the spillway. Yeah, sorry, getting the dimensions of the spillway into the DEM. It is quite important if you don't know what the rating is or what the discharge rating of that spillway is. So you do need to try and model it as much as possible with your wear coefficients and your widths and that type of thing put into the model just so you can increase your model accuracy. But if you have a rating table, it may actually just become a bit easier for you. Brandon, I don't know if you want to maybe add to that, but that's my 2 cents for that.
All right, thank you, Ernest. Yes, can we have a hand called, I think your name is Nomahuhu. You can just correct me. I have allowed your mic and you can unmute yourself and ask your question.
Thank you, Ashley. It's Noma Kuku. Thank you,
Right.
colleagues, for the great presentations. Brilliant job on getting those contours for the part that didn't have. My questions are all for Brendan. It's quite a few, but I'll be fast with it. The first one is how far downstream and also how far upstream do you need to clip your contours? If it matters, what's the appropriate distance if it matters? Another one is there another way to draw the cross sections on the flow? Also, how do you ensure that the cross sections are actually perpendicular if you draw them manually, like you said? Third one is, how do you know actually where the inline structure is? This is just out of curiosity. I'd just like to know, how do you actually know where it is exactly? How do you determine that? Thank you.
Thank you, Kuku, for your questions. What was your first question again?
It's how far downstream and upstream do you clip your contours for your model? If it matters, how far down do you go?
Okay. Usually only for high flood line of the dam, you're usually only interested in the area within the dam. So from where the river enters your dam and then up until your non-overspill crest level to your dam wall. But you can include a certain area downstream. It doesn't really matter how far downstream of the dam, just so that you can add extra cross sections downstream of your dam wall to allow acres to produce a stable model. Yeah, for your dam or for your model. I think for tailwater analysis, you would need contours for downstream of the dam, because what the tailwater is the tailwater analysis is to basically a high flood line for downstream of your dam wall. So, yeah. Can you repeat the other 2 questions again? Sorry.
Okay. The other one is how do you ensure that your cross sections along your flow, how do you ensure that they're perpendicular to the flow? And is there another way to draw them, or is it just manually only?
With the cross sections, there is a way to do it in Civil 3D. I've never done that method before. But yeah, there is a way you can do it in Civil 3D in terms of ensuring you don't have to be that accurate to draw your cross sections perpendicular to your contours. But yeah, you should try and be as accurate as possible. But you don't need to be that accurate when drawing your cross sections perpendicular to your contours. And then for the inline structure, how do you know the position of your inline structure? You usually put it where the spillway is located for your dam. Yeah. Does that answer your questions?
Yes, thank you very much, Brendan.
Okay, you're welcome.
Can I please just maybe come in, Brandon? Just a little bit of a note from our own experience. So in terms of the extent of the spatial data, I think it goes without saying, so my apologies if it's an obvious statement, but just ensure that when you, how can I say, it's a bit of a, sometimes it can be a bit of, how can I say, a subjective thing as to how big your terrain should be and your 2D area. But just an important thing is to make sure that when you've done your simulation, that the water is contained in your 2D area and you don't get any spilling out of your 2D area. And then in terms of the making sure that your contours, sorry, that the cross sections are perpendicular to the flow, If you were to do it manually, and it is actually a subjective approach, just based on my own experience, the contours can give you an indication as to, how can I say, where the water is going to go. So what tends to happen is if you have if your area tends to widen out and then come back in, you actually have to sort of like draw your cross sections perpendicular to the flow or to the direction of the river, almost going, how can I say, away from, almost sort of like facing out and sort of like, in a sideways direction, and then they sort of like bend and adjust as the topography actually becomes steep again as well. It really is a subjective thing, and from my own experience, you get better at it the more you do it. So just a bit of a point in that respect regarding those 1D, those cross sections, I should say. Thanks.
Okay, thank you, Ernest and Brandon. I just want to double check, Alan, is that an old hand or you have another comment? Okay, great.
Ashley, that's an old hand. There's a problem with my keyboard. Thank you.
All right, no problem. Okay, Rian, you are allowed to ask your question. You can just unmute yourself.
Thank you very much, Ashley, and thank you for the presentations. It was truly insightful. I just want to maybe get an idea that both presenters maybe keep track of the 1D and 2D analysis in terms of the time spent on the 1D and the 2D analysis. I'm just asking because the results were fairly similar from what I could pick up, and I'm just thinking about whether, especially for the indicative design or the indicative indication of the levels itself, whether it's worth it spending the time or the effort on the 2D itself. Maybe if they just maybe can allude to the amount of time spent on the 1D and the 2D analysis. Thank you.
Can I answer that one, Ashley?
Yes, I'm going to give both of you a chance. So, Brandon, you can start because you had a 1D and a 2D.
Yeah. So with the 1D model, the setting up of the model takes a bit longer than with the 2D. So when you're throwing in your cross sections or in your dam, that takes a bit longer than the 2D, because with the 2D, it's just specifying throwing a mesh around your dam, which doesn't take that long. But when it comes to running the simulation, your 2D model can take longer depending on the mesh size that you use for your mesh. So yeah, in terms of running the model, 2D is longer, but in terms of setting up the model, the 1D takes a bit longer than the 2D. Yeah.
Brandon, just to echo what you've just said, I agree with you. A 2D analysis in terms of the geometry setup does not take very long at all. Especially if you've got all your information on hand, I think you could probably spend less than a week. But I think it also depends on the complexity of your project. But certainly, when it comes to doing your simulations, get yourself some other work to do, because when you click run, you're going to be sitting for a few hours at a time. So yeah, that's just to echo and reiterate what you just said. Thank you.
Great, thank you, Ernest. Yes, and I think also the 2D, especially if you can use a terrain data. What is it now, Ernest? I'm losing the word. To determine your Manning's values.
Land cover.
Yeah, your land cover file, that at least takes away some of that uncertainty, where in your 1D you'd have to specify your Manning's values for each of your cross sections, but that's just a side note. Okay, I'm going to take a last hand and then we have to close the meeting. Caitlin, you can unmute yourself and ask your question.
Hi, everyone. Thanks so much for the presentation. I thought it was incredibly informative from both of the presenters. The question I have is for Brandon. I have a bit of experience with Hecra's 2D modeling, but I haven't actually done any 1D models before. So the question that I have is, when you are drawing your cross sections, how do you decide how close each cross section is to each other, and how does this influence the results in your model? Thank you.
Hi, Caitlin. Thank you for your question. In terms of drawing in your cross sections, the spacing between them, you want to keep the spacing between your cross sections as close as possible, because if you don't do this, you might get an unstable model. Because when NACRES does the calculation, it does an interpolation between your upstream and downstream cross sections. So yeah, when your cross sections are far apart, it could have an effect on the accuracy of your results. The closer your cross sections are to each other, the better. Yeah, I hope that answers your question.
Yes, thank you very much.
Sorry, if I could maybe just come in with a comment. So I think in the HECRAS manual, there is a guideline as to the spacing of your cross sections, depending on, I think, the river reach length and that type of thing. But just something just to take note of, and this is based on my own experience. It's good to try have as many cross sections as you can, but the problem is that cross sections are not allowed to cross and intersect. So that one just has to bear that in mind. It's good to try and load your geometry with cross sections, but they're not allowed to cross at all, which does become a bit complex when you've got a winding river. And trying to go perpendicular to the flow path, etc., etc. So just something just to keep in mind. Thank you.
Thank you very much.
All right, thank you. Yes, as like a last comment, I just want to say that usually 1D simulations are used for like low flow applications, and 2D simulations more for high flow applications. But I'll leave that up to all of you to go and find out for yourself which one you think is to be used. So we've presented all options, so you can use it at your own discretion. All right, thank you. Alan, last comments. I need to close the meeting.
Okay, last one, just to add to the presenters. We've done a couple of projects in Africa where the rivers were particularly windy, and we found if your sections weren't close enough, that means not crossing. We found that in the final results, if you didn't do 2D, you got super elevations, which actually messed up all of your design. If you're putting upstream, downstream retaining walls in the river, just say if there was a bend after a stilling basin on a 20-meter high gravity dam or something similar. So I thought I'd just add to that as a comment.
Thank you so much, Alan. I appreciate it. All right, thank you, everyone. I'm just going to take 2 minutes of your time to advertise for SANCOLD. If you're not yet a member, this is one of the cheaper voluntary associations you can be part of. So there's a website, SANCOLD website, it's displayed on the screen. And if you want to become a member, you can click on Become a Member and follow the steps over there. We have an SANCOLD short course coming up from the 4th to the 5th of November on tailings dams. So if you're interested in that, you can go to the SANCOLD website and go and get a little bit more information. And the registrations are open, so you can go and fill in your registration. Following that short course, we have the yearly conference and for SANCOLD, where we will be presenting a couple of papers and you can learn and gain some CPD points there as well. So if you are interested, it's from the 6th to the 8th of November in Johannesburg, and the registrations are also open. You can visit the website. Thank you so much for everyone that attended. We will see you at the next webinar. Thank you.
Thank you.
Thank you, Ashley.